Welcome back everyone to 7.4, Integration of Rational Functions by Partial Fractions. In this video we only have two examples, but they're long ones, so let's get right to it. Alright, in the last video I know we didn't have any irreducible quadratics, so let's get some irreducible quadratics in the mix here. So how do we determine if a quadratic is even irreducible to begin with? Well, we need to use something called the discriminant, right? So the discriminant was something back from our good old algebra days. It was defined as b squared minus 4ac. It's the thing under the square root in the quadratic formula. And if that's less than 0, the claim is your quadratic is irreducible. So, and remember, it comes from the quadratic formula. So b is 0. It's the thing next to the x term. A would be 1. It's the thing next to the x squared term. And then c is 1. It's the constant part, right? So that's for my specific quadratic. So in this case, it's -4, which is less than 0. So therefore, x squared plus 1 is irreducible. Okay, so we have an irreducible quadratic, and we have a linear part with an interesting exponent too. So the claim is the correct thing to use would be x squared plus 1, and then its numerator will be ax plus b, and then we have x minus 1s, right? So we need a different coefficient. We'll use c over x minus 1, and then d over x minus 1 quantity squared, right? Because it needs to take on all the values from 1 all the way up to the exponent, which in this case is 2. Okay, so then, well, we have a little bit of algebra to do now. And this will take up the majority of this problem. So let's assume that these things are equal. So that is that we have -2x plus 4 over, this denominator, which is x squared plus 1 times x minus 1 quantity squared. And this is equal to, well, my right-hand side. Ax plus b over x squared plus 1 plus c over x minus 1 plus d over x minus 1 quantity squared. Okay, let's multiply through then by the LCD, the lowest common denominator, which is x squared plus 1 times x minus 1 quantity squared. So on the left-hand side, we just get -2x plus 4. And then on the right-hand side, we have some work to do. Well, in this term, the x minus 1 quantity squareds don't cancel out, so we have to include those. For the c term, only one of the x minus 1s cancel out, so we'll still need this x squared plus 1 and another x minus 1. And then in this d term, well, the x minus 1 quantity squareds do cancel out, so what's left over is the x squared plus 1. Okay, now distributing time, right? Because we want to collect like terms. Well, in order to do that, we need to distribute this all the way out. So for this first term, let's just FOIL out this x minus 1 quantity squared. So we have to remember the inners and the outers, right? Don't just distribute the squared. That'd be wrong. In the second term, let's go ahead and FOIL again. So x cubed minus x squared. Let's erase these really quick. And then plus x and minus 1. I'm always paranoid that I'll make some mistake here. And then we need to distribute the d. That's the easiest one so far. Okay, now we need to expand this ax plus b times x squared minus 2x plus 1. So again, distribute this all out. I'll do the a's first, carefully making sure not to make any mistakes, or at least very few mistakes. All right, and then how about when I distribute the b terms? So that's bx squared. Let's see, that's going to be, minus 2bx, and then plus b. And then finally, we'll distribute the c terms, the c. So cx cubed minus cx squared plus cx minus c. And the d stuff stays the same. Okay. On the right-hand side, let's see. We have cubed terms, we have squared terms, we have the linear terms, just x to the first power, and then we have the constant stuff. So let's start to group these things, right? So all the cubes, where are my cubes at? Let's see, I have one with an a and one with a c in front of it, and that looks like about it. So a plus c times x cubed. All right, how about my squareds? My squareds, yes, here are quite a few squareds. All right, so let me write first, maybe I'll do b since it's positive. minus 2a minus c, and then plus d. Yeah, minus c, sorry, and plus d. There are all my squareds. And how about my linear terms? So there's this a, there's this minus 2b, and there's this c. So a minus 2b and c, and I think that's all my squared terms. Oh, sorry, linear terms. Blech. And then finally my constant terms, b minus c plus d. I'll go ahead and highlight those. All right, now I got them all. So let's see, let me copy and paste this. Just write it again here. And remember, in order for these to be equal as terms of functions, well, we need to make sure all of their coefficients are equal. So 0 needs to be a plus 3. 0 also needs to be b minus 2a. Oh, it looks like I forgot my x squared term. Minus c plus d. Let's see, negative 2 needs to be the same thing as a minus 2b plus c. And then 4 needs to be the same thing as b minus c plus d. Hooah! So we have quite the system of equations here. Again, let me write these all out. A plus c equals 0. B minus 2a minus c plus d equals 0. A minus 2b plus c equals negative 2. And then b minus c plus d equals 4. So this is a system of equations, 4 equations, 4 unknowns. So let's get to it. This first one says that a is equal to negative c. So now let's write this into our other equations. Everywhere we see a negative c, we're going to put an a. So in this case, it has a negative c. So we're going to put plus a. So that's going to be just b minus a plus d equals 0. All right. In this one, let's see. We have not a negative c, but we have a positive c. So that's the same thing as negative a. So a minus a. That's nice. We get negative 2b equals negative 2. So that implies that b has to be 1. That's nice. Okay, and then finally here, instead of that negative c, I'll put an a. Okay, and now looking at these, well, actually my second and my fourth equation, at least my second and my fourth line, let me just highlight these really quick. These look like we can actually do something with them. So yeah, let me highlight these. These look very close indeed. So let me rewrite those here down below and see what I'm talking about. And I'm gonna rearrange the order so hopefully you see it too. So this first one, I'm gonna rewrite it as negative a plus b plus d equals 0. And then the second one, I'll just leave it as is, a plus b plus d equals 0. Oh, sorry, equals 4. Yeah. We can rewrite b's as 1s because we know that. And now let's see what happens when I add these two equations together. Right? Because then the a's cancel out, and I get 2 plus 2d equals 4. So therefore, 2d equals 2, so that's the same thing as d equals 1. Let's go ahead and use this last equation then. This last equation, knowing that b equals 1 and d equals 1, we can write it as a plus 1 equals 4. So that means that a has to equal 2, and since a is the same thing as negative c, well, we know that c has to equal negative 2. So there are all of my coefficients. So I can solve this out. It takes a little bit longer, but I can do it. So therefore, let's go ahead and plug these back in. I now know what a, b, c, and d are. So my original integral up here can be expressed as the integral of, and now a is 2, so it's the integral of 2x plus b is 1 over x squared plus 1. And then c is negative 2, so negative 2 over x minus 1. And then d is 1, so 1 over x minus 1 quantity squared. All right. And now some of these I know very quickly how to integrate, and others it takes me a little bit. So I think this first one's difficult, or at least more difficult. So let me hold on to this for just a second. The second one I can integrate. This looks like the classic natural log. thing. So this is going to be -2 times the natural log of the absolute value of x minus 1. And then when I integrate this thing, this is really has like a negative second power. It becomes this 1 over x minus 1, and we need that negative in front of it, plus the c. And of course, you can take the derivative and verify that all this is true. So then the big question is, how do I integrate this first thing? And this may be a good point to pause the video and try some things yourselves. And when you're ready for the answer, come back. But the idea here is that we're going to split it up. So if I split it up like this, the claim is I can integrate these pieces. So this second piece, we should recognize this as our good old friend, arctangent, or tangent inverse. Right? So I'm going to write tangent inverse of x. And now this first piece, again, stare at it for a little while, but we should think, this is the classic old u substitution, actually, where u is going to be this x squared plus 1, and then du happens to be 2x. So it turns out this is actually equal to the natural log of the absolute value of x squared plus 1. And you can double check, right? Take the derivative of this. You get the same thing. Okay, so that's how we integrate this first part. So now let's go ahead and take these piece and put it back into our formula up here. I'm going to cheat and use technology here, so copy, paste. So that's the first integral, and then we just copy and paste this. Ooh, looks like I still didn't leave myself enough room. And there is our final answer. So this one took a little while, as you would expect, because it has the irreducible quadratic and it has linear terms with higher degree powers here than just 1. So it does take a little bit, but we can certainly do it. Okay, let's talk about another remark. Here in the case where our rational functions, well, the degree of the numerator is greater than or equal to the degree of the denominator, right? So in all the previous ones, we've always assumed that it was less than the degree of the denominator. So if this is the case, we need to include a 0th step. And that 0th step is to divide the rational function using polynomial long division and express it as a sum of a polynomial and a proper rational function. So we can indeed evaluate out rational functions where the degree of the numerator is greater than or equal to the degree of the denominator, like this one here. And the thing that we need to use is just polynomial long division. So if you need to review polynomial long division, I would suggest you do so. I'll go over it quickly here in this example. Okay, so polynomial long division. I'd like to divide the numerator by the denominator. Now we need to set this up like we did in the good old days of long division. So, divided by the denominator. And we need to ask ourselves, when we do polynomial long division, what do I multiply by x to the 4th, which is this leading coefficient, this leading term here, to get x to the 5th? What do I multiply by x to the 4th to get x to the 5th? Well, that's x. So I need to multiply by x. So if I multiply this thing by x, I get x to the 5th plus, and you have to do both pieces, and you get x cubed. Notice how I line these up for subtraction. So now when I subtract, well, x to the 5th minus x to the 5th, 0, great. And then 7x cubed minus x cubed, 6x cubed, and the rest stays the same. Okay, now I ask myself, what do I multiply by x to the 4th to get 5x to the 4th? Well, that's 5. So let's add 5 here. 5x to the 4th plus 5x squared. Remember, I line these all up and I get ready for subtraction. So remember, we need to subtract away all of it, just like in the good old days of long division. So 6x cubed, and let's see, this is going to be negative 4x squared, because I'm subtracting my 5, and the rest stays the same. And now I'm done, because this degree, this x cubed, is smaller than x to the 4th. So therefore, we can write this thing as x plus 5 plus the remainder, which is the 6x cubed minus 4x squared plus x minus 2 divided by the denominator, which is x to the 4th plus x squared dx. Okay, so now we have our function set up right? And the degree of the numerator is now less than the degree of the denominator. So now we can go back and we can do the partial fractions that we know and love. So the first step of partial fractions, factor the denominator. So if we were to factor the denominator, in this case, well, there's an x squared in both terms. So we can take out the x squared, oops, and this will be x squared plus 1 left over. We've actually seen this quadratic before, right? This is an irreducible quadratic. So I need to assume that this thing can be written of the form ax plus b over the irreducible quadratic, x squared plus 1, plus c over x plus d over x squared, right? Because it takes on all of the powers between 1 and, in this case, 2. Okay, and this should be equal to my right-hand side. Now, just as before, we're going to multiply through by this LCD, and that's going to be x squared times x squared plus 1. So in my first term, well, the x squared plus 1s are going to cancel out, and I'll just have the x squared. My second term, not much cancels out, right? So I'll have the x times x squared plus 1. And then in my third term, the x squareds will cancel, so I'll have x squared plus 1 left over. And on the right-hand side, it stays the same. Just barely fit. All right, now expand this all out and collect like terms. So expanding time, ax cubed plus bx squared plus, and let's see, I can do this, cx cubed plus cx, and then plus dx squared plus d. And this is equal to my right-hand side. And now, just as before, I need to collect like terms. So I need to look for my cubes. So it looks like a plus c is my cubes. How about my squareds? It looks like I have a b and a d, both positive, b and d. How about my linear terms? Just the c it looks like. And my constant terms, looks like just a d. So in order for these to be equal as functions, remember that the coefficients need to be equal. So that's to say that our a plus c needs to be equal to 6. Our b plus d needs to be equal to -4. Our c needs to be equal to 1, it looks like. And then our d needs to equal to -2. Ooh, I like this system of equations. This is a nice one. A plus c is equal to 6. B plus d is equal to -4. C is equal to 1. And d is equal to -2. So you can see I already have c and d solved for. And if I plug this in up here, that gives us a equals 5. And if I plug in d into the second one, let's see, I get b minus 2 equals -4. So add 2 to both sides, and I get b is equal to -2. So there we go. We know a, b, c, and d. Like I said, that was a nice one. So now let's go ahead and plug these in. I have the integral of, I can't forget about my x plus 5. Plus, and now this thing right here, we've used partial fractions to rewrite it as ax plus b, so that's 5x minus 2 over x squared plus 1, plus c, which is 1 over x, and plus d, which is -2 over x squared dx. So now I can integrate this thing. All these pieces, the claim is I know how to integrate them. The only one that's a little bit difficult is this third one, maybe. So I can integrate x, 5, but in order to integrate this one, let's split it up. I'm going to split it up in kind of a clever way. I'm going to write this as 5/2 times 2x over x squared plus 1 minus 2 times 1 over x squared plus 1. And so this first part, this 5/2 times 2x over x squared plus 1, this is clever just so that way we can set it up for u substitution, right? Hopefully you can see this -2 comes from, and then this 5/2 and this 2x would cancel out, and that would give you 5x. So again, we're setting this up for u substitution. Okay. Plus 1 over x minus 2 over x squared. I'll pull this 2 off to the side here. And -2 over x squared. Okay, integrate this thing. I get x squared over 2, 5x. And now as we saw from the last problem, this is going to be the natural log of the absolute value of x squared plus 1. That's why I did that trick there. Minus 2. This is arctangent, again, like we saw from the last problem. Integrate 1 over x, I get the natural log of the absolute value of x. And integrate 1 over x squared, and I get negative 1 over x. So negative negative makes positive. And I get my constant of integration. Let's rewrite this a little bit just to make it cleaner. And that is my final answer. All right, and I think that's a good place to end right there. As you can see, I mean, the long division wasn't that bad in this problem. The solving the system of equations wasn't so bad. There were just a lot of pieces, essentially. All right, but that ends 7.4. Next time, we're actually skipping to 7.8, improper integrals. So I'll see you soon.